All right, coffee is done and we can begin. So, all our previous webinars were about how to solve cases more or less in automatic way when the device is known, when the device is supported, and all you need to do, you need just run some automatic searches, and VNR can find page structure, BCH codeword, XORed key, and so on. And we finished that series of webinars like about automatic solutions, more or less automatic way. Now we will have several ones about cases when VNR may not have resources when for some particular device, when you may get some new device, unknown device, and the database may not have all resources for that device. And in that cases, you need to do some manual steps. Today, we'll talk about two of these steps, page layout and ECC. So after you get a physical image, the first, well, almost, well, if you don't have bed columns, the first step would be page layout. It refers to set manually where is data area, where is service area, and ECC. After that, you can try to apply ECC, and if there is no code words in database for this particular device, you can try to find to build that code words by yourself. So today we will talk about two of these things. First, it's page layout. As I said, page layout step refers to setting borders of data area, service area, and ECC. And to be able to set the borders, we need to know typical page structures. And by the way, let me send you the document. Yes. This slide shows typical page layout structures. And all you need to do is just more or less remember the typical structures in order to be able to set the borders for your, let's say, unsupported device, or for the device that for some reason you don't know, you don't want to use automatic way to set the borders. And the main thing you need to remember here, first of all, it's a distribution of data areas, service areas, and ECC areas for different controllers. You can see that Phison, AU, CBM, and so on controllers, they have the first type of page structure. Silicon Motion and InnoStar another one, and SanDisk has own structure. And it's the first thing you need to remember. Typical allocation of data areas, service areas, and ECC within page. The next thing you need to remember, it's sizes of that structures. The first structure is data area. And you should know, you should remember that data area, it's a constant within the page. It means that size of the data area will be the same within the page for all these data area pieces, like first data area, second data area, they all will have the same size. And that size may be, data area may have three types of sizes, three sizes. The first one is 512 bytes. It's typical for quite old devices. Next one is 1024 bytes. It's kind of standard for now. And 2048 bytes. This size is typical for SanDisk controllers. So that's sizes you should remember. And if you will know these sizes of data area and typical distribution for different controllers of data area and so on, you can easily do the page layout thing. you should just set first data area, then ECC, and so on. Well, I'll show you how to do this on the next steps. So data area has standard sizes. ECC area. ECC area may have different sizes, but one particular device will have just one size of ECC area. I mean, if first ECC area has size of 42 bytes, the next one will be 42 bytes, next one will be 42 bytes. So all ECCs will be the same, will have the same size. I mean, at least for data area. The same for phasing controller. If first ECC has 42 bytes, then next ones will be the same. So ECC is a constant within the page. But size may be very different. One device, some old device, may have 10 bytes for one data area or data plus service area. And another devices may have 230 bytes. Well, that's usually typical. It's typical for SanDisk controllers. And taking into account that this amount of bytes belong to 2048 bytes. So we understand that it's approximately 115 bytes belong to 1024 bytes. So it's more or less standard size of 1024 for 1024 bytes of ECC area is 100 bytes plus minus. It's for modern controllers. 100 bytes of ECC for 1024 bytes of data area. And the last thing here, it's a spare area or service area. And it also may have different sizes, and sometimes it may even have different sizes within one page. Like it's very typical for phasing controllers. The first service area may be bigger, next service area, and all next service areas may be smaller. Sometimes next service areas may not exist at all. So they may have size like 0. But yeah, in case of Silicon Motion, we have just one service area, so it will be just one size. In case of SanDisks, it's also quite a standard, but for phasing controllers, it could be different. So service area may have different sizes even within one page. And those three typical structures, they are most popular for. You can see that. You can see here a list of most popular controllers. Here on this slide, you can see another structure that you may see sometimes, or that may have sometimes. The first one belongs to quite old controllers. We have here 4 data areas that go in row, and then we have 4 service areas, 1 for each data area, and 4 ECC areas. Same, 1 for each data area and ECC and service area. It's typical for quite old controllers. And another structure here, it's for ATG controllers. If you do some forensics, sometimes, well, even not forensics, if you deal with voice recorders, you may know that many of them use ATG controllers, and those controllers use this page structure. So this one is typical for ATG controllers. And the same rules here. Data area is constant, ECC area may be different, spare area may be different. So that's the thing you need to remember about page structure. If you know this, it's not a big problem to do page structure, page layout for basically any controller. Next, several pictures shows you more precisely typical sizes of data area, service area, and ECC. So for Phison controller, you have these sizes. And as I said, first service area may be bigger, next service areas may be smaller. ECC may have size from 10 to 126 bytes. And data area, well, usually it's 1024 bytes. Silicon Motion and InnoStore have this structure and quite same range for ECC and for service area. SanDisk is represented here. Alcal Micro and Chips Bank next. And here, then we have Toshiba and SSS controllers. And ATJ. So I hope that these pictures may help you to do page structure for some device if VNR doesn't do this automatically. And then this slide shows you like order of clicks that you need to do. First you run bitmap viewer, then you run structure viewer, then you do double click on that undefined area. You go inside the page, and then you add new structure. I'll show you all these steps later. Well, actually, I think that I'll show it right now, and then when it will come to BCH Codeword, we'll switch back to the presentation. Okay, now let's do the page layout thing. Okay, I'll switch the screen. Okay. So very typical controller, very known. We're very familiar with this already, I believe. So let's say that we don't have this yet, we have just physical image. If we open physical image, we can see here, we can see data here. If we run structure viewer, we have a block structure because VNR takes it from memory chip configuration. It's written in configuration. We have page size because VNR also knows the page size. And on this stage, VNR has no idea about internal page structure. VNR doesn't know where is data area, ECC, and so on. And we can set it. So since this is Phison controller, we know that it starts from data area, right? So we know that from the beginning, we have 512 or 1024 bytes of data area. And now let's just scroll it horizontally in order to find some patterns. And if service area is not XORed, we'll see service area pattern, and the task is really simple in this case. We can just point the mouse to the last byte of the data area. So we understand that this pattern, it's a service area. I hope that you know this already. So we point mouse to the last byte of data area, and we can see that in this area, you see byte position. So now mouse is on the last byte, and on byte position, we see 1023, number of byte 1023. So that means since we count from 0, the total amount of bytes of data area is 1024. So we just proved that the data area here is 1024 bytes, and we can add this data area here in the page structure. To do this, I may double click on the page, then here I select data area. When you start new case, new task, default size of data area is 0. So you select it and the length is 0. You change it. You should change it. So you set 1024, and in this area you set position or addresses of the data area. Start address is 0. Stop address, you can set it manually, 1023, or you have here 3 buttons which will help you to set that address automatically, more or less. This one, full area, means that it will set this size for full area. So it's like it will set first 1024 bytes is data area, then next 1024 bytes is again data area, again, and until the end of the page. So full area will be allocated as a data area only. And of course, it's not correct, it's wrong, so we don't do this. This selection button will set here address of the selection that we made before, I mean, the place which we clicked by mouse. I usually don't use this. Usually we use this button, structure length. So stop address is calculated based on start address and the size of structure. If start address is 0, total size is 1024, then stop address will be 1023. If I click it here, I have it like calculated in this field. Then I click to OK, and I have the structure now. And the VNR has option to color different structures. So you can control borders quite easy. With colors, it's quite easy. The color is finished here, and you can definitely understand that data area is finished here. So what's next? After the data area, if you remember, we have first service area, right? Okay, so let's check how many bytes we have for this, and then we will proceed. So, service area, I can zoom it in, and actually I can just count how many bytes I have here, like 1, 2, 3, 4, 5, 6, 7, 8. Or I can make a left click within. By the way, these lines like orange, yellow, and orange, they represent 1 byte. I have here 8 pixels, 8 dots. 1 dot is represent at 1 bit. 8 bits, it's 1 byte. So here in line I have 1 byte, and I can make a left click within any place of first byte and right click in the last byte. And here I can see how many bytes selected right now. It's 8. And the important thing here is to make a right click on the same page, like the first click, because if you will make first click in one page and next click in this page, you can see that selected here amount is very big, because it's actually count all bytes from here, then it's going until the end of the page, then it takes next page, next page, next page, and then this page, it takes all bytes from this page until this cross. So both crosses should be within the same page if you want to calculate the amount of bytes within one page, like I do now. Okay, so it's 8 bytes here, and I can just set service area 8 bytes, size of service area 8 bytes. Several words about this list of structures. So here in this area, we have actually like a scheme of structures, of structure allocation, of structure distribution within the dump. So on the root level, it's a dump itself. So now we are like on root level, on dump level. Then dump, if you remember, consists of blocks. We divided by blocks. And if we do double click, we go inside one block. So now it's one block which consists of 256 pages. Then we do one click again, and now we are within one page. And now we are doing page allocation, right? Page structure, description. And so here we have scheme of structures distribution within the dump. And in here we have list of that structures. So here we have block, page, data area, ACC, header, and so on. And you can also pay attention that from the left side we have that names of structures, and here we have written like S block, S page, S data area, and so on. So we made this for next purposes. You can create any structure you want here in this list, and you can call it whatever you want, however you want. But for VNR, VNR uses a standard list of standard structures. It's necessary for VNR to know what is block actually, what is page, what is data area, and so on. So you can create any structure here, like you can call it any, and the length will be like 50, for example. And you can use this any structure however you want. But if you want that VNR uses this structure as a data area, because VNR should understand that this any is actually, you want this to apply it as a data area. Then you do right click and select option here, set as a data area structure. So now this data area is not data area structure anymore, and this is data area structure. And when it comes to use data area structure for VNR, it will take this record for the data area, and this one will be ignored. So if you add some new structure as a data area, you should care about if there is another structure and it's selected as a data area, for example, also as a header, and so on. Let me set it back to the data area structure, and this one could be deleted. So the thing is that, let me summarize, there are standard structures. Here it's LBN, header, LPN, ECC, block, page, and so on. And you can assign to this standard structure anything from like any structure that you will create. But when you do this, you should like understand what you are doing, and because later it may confuse you, and VNR may not work if you, for example, add like data area, let's say, data 1, and you set it size 512, and okay. So you have data 1, you assume that you use this data 1, and you use this data 1 in the, let me remove this. Now you select this data 1, and you set it 1023, like stop address. So you have here two data 1 structures from 0 to 1023. But now VNR will not work, because for VNR, this data 1, it's something but not data area. As a data area, it takes this record. So for VNR, there is no data area structure now in this allocation and this scheme of structures. All right, I hope that it's clear, more or less. Well, let me remove this one and remove structure, this one. And let's continue. So, yeah, and by the way, once you're at the very beginning, when the size is 0, you can change, you can set this size. If you remember, I did that. And that size will be applied in this list. And if you did mistake, for example, if you set 1023, so 1023 will be here. And in order, if you will try to change it on this level, like you select data area, you see you can't now switch it to 1024. Oh, well, let's imagine that we have here 1023. Okay, let me just do this. Remove record, and let's say that you set here 1023 by mistake. So now you select here 1023, and it's not available here the option to set 1024. So to change it to 1024, you should go to this list of structures and click to edit structure, set 1024, and okay, now it's good. Okay, so data area 0, 1023, and yeah, we have it. The next one, it's a service area. Service area is not a standard structure. It's this structure is used mostly for our convenience. And actually, in fact, the main thing in service area, it's a header and LBN. And in fact, if we know where is the header, we can just do like this. We can set header, let's say first byte here. Then we know that there is one empty byte, and then we can set, we know this from our experience, let's say. And now I set LBN for these 2 bytes. Then I can skip these bytes as empty, these 3 ones, and continue with ECC. If you like this way, you can go like this. If you don't like it, there is another way. It's, in my opinion, a little bit more clear. Let's say remove record, remove. So you can do like this. You can create a service area structure, and we know that this is 8 bytes, right? So now we have for all these 8 bytes service area, and then you can jump in the service area, and already here you can set where is the header. It's the first byte of service area. Oh, you see what happens when you use option full. It just takes full area and set everywhere that header. So it was a mistake. I should use this button. So start address 0, stop address the same, and I have here the header. And LBN will be here. So that's another way. And on this level, you have data area, service area. Then we have ECC. Inside the service area, we have service area structures like this. Okay. After the service area, we have ECC, right? And now let's see we don't know size of ECC, right? There is no clear border. Well, actually, we can search for that border. Maybe we can search for some patterns, and at some moment we will find it. But if you have XORed dump, usually you don't see that border. And the question is how to understand how many bytes you have for the ECC. And there are two approaches here. The first way, it's just math. We can check how many bytes we have from this service area until the next service area. So I make left click here, and then I switch it horizontally to the next service area. Yeah, here, and made right click on the last byte. And you can see that now I have selected 1066 bytes, right? Let's switch back to this. So what I did, I just measured amount of bytes from this point until this point, right? So this area. I know data area size. It's a 1024, right? It's a standard. So if I know whole area size, if I know data area size, I can very easily calculate ECC size, right? And let's do this. So it's since total size is 1066, I ran calculator. Okay, it doesn't work for some reason. Well, anyway, 1066 minus 1024, it's gonna be 42 bytes, right? It's gonna be 42. And now we understand that for ECC size is 42 bytes, right? Okay, let's say that ECC is 42. Once again, I got this number with the calculator. I took 1066 bytes minus 1024 bytes, size of data area, and I got 42 bytes for ECC. The rest is ECC. Okay, so now let's see it. If I run this option sync position, VNR will bring me in the bitmap to the area which I selected here. So this is service area now, and we can see that ECC is going from here to here, and then I have data area again. So now, since I have already data area in the list, I can just select data area. Start address is automatically selected. It's the first byte of that undefined area, of the area where I did the click. And here I still use this button. And you can see that data area is finished exactly in the place where next service area begins. So so far it's so good. It's all good until now. Then I have next service area. And next service area, as you can see, it's smaller than the first one. First one was 8 bytes. This one is just 1, 2, 3, 4. So that's what I was talking about. Second service area is smaller. So that's why I should create new service area structure, because if I use this one, its size is predefined already. But if I will write one more symbol like service area 1, I can set the size. And now it's coloring 2. I said that the ECC size is the standard. So next ECC should have the same size, 42 bytes. Like this. And let's set one more data area. And we can see that it's all good, it's all right. So now I don't have any shifts, everything is on position, and I know that this size of service area should be the same until end of the page. So I can use this size to fill up the page until the end. So after the data area, I have, what do I have? I have service area 1, right? So service area 1 is here, and then ECC is here. And these three structures, it's just, it's like a one full period, right? Data area, service area 1, and ECC. And now I have two options. I can select these three structures, copy them, and then I can paste it, and it will just paste one structure. Or there is an option paste till the end, and it will paste multiple times this same structure until it's possible, so until the end. And we can see that ECC is finished here. So it's all good, it's all right. Page layout is done for now. And basically, that's it. Okay. I just wanted to ask if you have questions. So we do have one. Okay. So what's the question?
Sir, I want to ask that when we are doing an unknown controller, like this we know is a Physion. Otherwise, if it's not a known controller, we see that we have service area and we have the second service area. How do we come to know that ECC is after the first service area or before the second service area?
Well, because we don't have any structure here when ECC is located before data area. Oh, sorry. When we have data area after the service area, and then we have ECC, and then again the service area. So typical structure is always like this. We have data area, service area, and then ECC. We don't have here situation when we have data area, then service area, then again data area, and then ECC only.
Okay. And another question I have is that what are those 79 bytes that are left in the end of the page? I see it with so many controllers.
It's just unused area of the page. If you remember, maybe I told once that page size, it's a physical thing. It's a physical amount of bytes, physical amount of transistors. And if developers of controller decided that they don't need full page, all these transistors for the area for ECC, for example, they just left them unused. And they just write data until this point, and this area is just not used. It's still empty. No data was written into this place. Do you understand?
Yes, sir. I understand.
Mm-hmm. Okay. Any other questions? How can detect LPN? Well, LPN usually looks like, usually we don't need to detect them for majority of controllers. But if LPN presents, you can see it visually. I'm gonna show you this now. So let me do a new share. So in our knowledge base, you can check this article binary patterns in non-flash memory. And here you can see how data area looks like, how XOR looks like, and how LPN looks like. And LPN looks like, you see this counter, and it's different from page to page. So each page has LPN, it's logical page number, right? So each page has different number, and that's why you can see this like stairs here. This is LPN. Should I detect the block size? I did discuss this question in some previous webinar. I don't remember which one exactly. Basically, you shouldn't, usually you shouldn't, but sometimes you need to check if it's correct or not. Because sometimes configuration of the chip may have physical block size. And in case if multi-plane page allocation was used, logical block size or virtual block size will be different. It will be bigger, and in this case you need to adjust that size. You need to check it and adjust here. And this question was discussed in the webinar about multi-plane page allocation. So I showed there how to check it, how to adjust it, and yeah, it was discussed there. And also that the block size thing is shown in the article in our web, in our knowledge base. It's shown here in this article, physical and dynamic XOR. In this area, this virtual block. And there it's shown how to check block size, why it may be different, and so on and so on. So please check this article and previous webinar. The question, do you need to set the header and LBN only once in only one service area? Yes, you can set it only once. You should set it only once. But moreover, you may not set LBN and header at all in service area. You do this just for your convenience, because you see LBN and header here, you set it, and then software knows at this stage where is header and LBN. But in fact, software doesn't need to know these structures in the page structure. The main thing where software should know about LBN and header, it's parameters of markers table. Parameters of markers table. So we must have LBN position and header position in here. So you have two ways. First way, you can set LBN and header on this stage, on this step, when you do page layout. And then you only need to, let's say you don't have here, okay, let's destroy the table. You don't have here LBN, but when you do have LBN in the page structure, you have it in drop-down menu in here. You don't have it for some reason. LBN, yes, LBN. Ah, yeah, because I need to, okay, copy structure. I need to connect physical image because structure now is here. So now it's going through this chain to the markers table. And when I click on this checkbox, so markers table took structure from the physical image, from previous elements. Now if I make, yeah, now I have that LBN in drop-down menu. And if I select it, it will take automatically those bytes to this field. But it's basically not necessary to do. If you know the positions, you can type them manually, 1026, for example, 1027. And it will have the same effect like you do it like this. Okay, and now the second part of the webinar, it's about BCH code word detection. So first of all, what is BCH code word? BCH code word, you can assume this as like a set of parameters for BCH correction, for bit errors correction. And that set of parameters includes several things. You can see it on this slide now. So let's talk about them more detailed. So first of all, it's a payload area and parity area. Payload area, it's the area which is protected by ECC. So the area where we do fix bit errors. And payload area, it could be either data area only, in case of SM controllers, for example, or it can be data area plus service area, in case of FISM controllers. That's payload area. Parity area, it's a parity area, it's the area of ECC. The area where we have ECC code which helps to fix bit errors. So that's a payload area and parity area. Then polynomial. Polynomial, it's like a formula which is used to fix, to calculate ECC, to create ECC, and then to fix bit errors. We have here 5 versions of polynomial, and it's like most used versions. Of course, there are more of them, but usually for BCH, for BCH in NAND, the developers used 5 versions of polynomial mostly. And it's here. And then we have options for inversion and bit rotation. So sometimes it's necessary to invert data before ECC correction and then invert it back, or to do bit rotation. So it's like data preparations for BCH correction only. And if it's necessary, you will have here to set these checkboxes. If it's not necessary, you just skip it untouched. So that's the parameters of Codeword. And we can understand that from the previous step, we kind of know already where is payload area and where is parity area, right? Because we could see this. So we don't have any questions about this part. But we don't know which polynomial exactly is used and if it's necessary to use inversion or bit rotation. And basically here, since we have 5 versions of polynomial and on-off options for inversion and bit rotation, in total we have 20 combinations to try to detect correct code word. In case if it's quite a standard code word. So usually this approach may be used if you have some device where standard polynomial is used and that inversion bit rotation things, but size of ECC is a little bit different, let's say. So we have in database code words for ECCs like 42 bytes, but your particular device has ECC 46 bytes, let's say. And then the code word from a database will not work. And you need to adjust it. And to adjust it, it means that you actually need to create new one. So you set here payload area, start to stop address for payload area, for parity area. Then you select a polynomial and inversion bit rotation thing. How to select correct polynomial and inversion bit rotation? Well, you can go to database and just check which polynomial is used for similar controller, because similar controllers usually use the same polynomial. If you don't want to do this, you can just try all of them. As I said, it's 20 combinations in total. You just try them and one of those may work. So that's the thing what we do when it comes to detect BCH code word. The next slide shows you more visually what is payload area and parity area for different controllers. So for this type of controllers, payload area is here, then we have parity area. For Silicon Motion, it's located like this, and for SanDisk, we have this structure. So having this slide and knowing where is data area, service area, and TCC, you can very easily detect where is payload area and parity area. And as I said, there shouldn't be any questions about this part. Now polynomial. As I said, we have here 5 main versions of polynomial. Polynomial is a formula that are mostly used for BCH correction for NAND devices. And if you will click on this drop-down menu, you will see that list of numbers, and one number represents one polynomial. And it's a that polynomial thing and BCH correction, it's quite complicated thing. You need to have quite good math background to understand all of this. But to use this thing in the VNR, it's not necessary. Here I just showed what is those numbers. So this number is actually represented this formula, and this polynomial is one of the polynomial which is mainly used for BCH correction. There are a lot of information on the internet. You can read about this if you are interested in, but to use these things in the VNR, it's not necessary. You just need to understand in general what is polynomial, payload area, parity area, and that bit rotation inversion thing. So that's the polynomial. And yeah, that's all we need to do until now to try to detect code word. And now let's see how do we do this on the real cases. So we have here physical image. Now I bring ECC element here. And normally, if you remember, I should click here, find code words, and software will try to apply all code words from database. And if one will be good, it will say you that that's the correct code word. Let's assume that there is no good code word in database. It's a different device, a new device, and you need to do it by yourself. How to do this? Here in parameters of the ECC element, you have this field for the code word, and now it's empty. So to add new code word, you need to click on this pencil button, and new window will appear. And in this window, we should have list of code words. One code word is supplied for one payload area plus parity area. So if you have like this structure of the page, one code word should be made for one payload area plus parity area. If you have 8 such periods, then you should have 8 code words, because as you understand, each code word has own payload area address and parity area address. Polynomial and inversion and bit rotation will be the same, but addresses will be different. So that's why we should have one code word for each payload plus parity areas. In case of 8 kilobyte page size and 1024 bytes of data area, we will have 8 code words. In case of 16 kilobyte page size, it's going to be 16 code words. Okay, now let's go back to the VNR. And it's convenient to do this procedure like this. So I open physical image structure view like this in order to see addresses of data area, service area, and ECC here. And now I can go to ECC, click on this pencil button. Here I have listed code words, and I can click on this plus button to add the new code word. So here I have that window where I set parameters of code word. And payload area, first thing I need to set is payload area. I see that it starts from 0, right? So I just set here 0. Then stop byte address. It's a last address of payload area. And which one is the last one? Since this is Python controller, payload area, it's the area of data plus service area, right? So I take last byte of the service area. It's a 1031, right? 1031, it's the last byte of payload area. And parity area goes right after the payload area. So it's 1032 parity area, and stop byte address would be this one, 1073. 1073, it's the last address. And now polynomial. So I can just take the first one, and I can try it without inversion and without bit rotation at first. Then I need to try it with inversion only, with bit rotation only, and with both. And I will repeat this routine for each polynomial until I will find the good one. Okay, so now I click OK. Now how to check if it's good or not? I need to run ECC map here. and check colors. And red colors, you can suppose you can understand that it's bad. It's not correctable. So this code word doesn't work for this device. Okay, let's change it then. I click through this pencil and then select code word, and there is option here, edit. So edit, and let's set inversion only. Inversion only, and now when I click through OK, it's automatically applied, and you see it's still red, so it's still not good. Then I try bit rotation. Well, with the new version of utility, we have many types of bit rotation, but the first one is mostly used. So we will use this one. Those one usually we added them maybe for future proposals. Until now, we saw just first two of them, and the first one is most popular, most used. So we use this one. So only bit rotation. Okay. And it's still red. And then edit, and I will enable both inversion and bit rotation. Still not good. Okay, so this polynomial is not good for this device. Let's take the next one, this one. And again, without inversion and bit rotation. Okay, not good. Inversion only, not good. Inversion and bit rotation. And now it works. Now it's all green. That means that this is correct, good code word for this device. So I found polynomial, and I found like tweaks or options of data preparations that I should apply for data in order to make a BCH correction. So, and first code word is ready, but if you see, I have more of them. So now let's do the second code word. I click to the plus button, then payload area. Start address, it's the first byte of second data area, it's a 1074. And stop address, it's a last byte of second service area, it's 2101. 2101. Then parity area, it's a second service area. It's 2102. 2102. And the last one, 2143. 2143. Then polynomial, it was this one. Inversion, bit rotation, okay. So it's still green one. Its color was changed because here we see, here one square represents one page. And we can see worst result for the page. So now we have two code words, and before it had different picture with one code word. With two code words, it's changed because maybe second code word maybe may have second payload area may have more bit errors, and that's why it's like worse than the first payload area, and that's why now we have more light green colors here, because we have a worst result of code word for one page. Okay, so the second code word is done, and we can proceed with the next one. But you actually see that sizes of service area, of payload area, and parity area for next code word will be the same, right? Because service area is the same. So we have option here just to create new code word based on addresses and sizes of the previous one. This option, and new code word from add next code word from selected. So once you click here, it will add new code word with the same polynomial, same data preparations, and same size of payload and parity area, but with different addresses. By the way, what syntaxes do we see here? First pair of numbers, it's address of payload area. Second pair of numbers, it's address of payload area. Then we have size of payload area, size of parity area, polynomial, and data preparations, inversion and bit rotations. Okay, so to add next code words, all we need to do, just click several times. Oh, this one is already not necessary here because it's 9 code word. So I remove it, and I have 8 code words. I can close it and ACC map, and it's all correctable now. So code word is ready. And if we didn't have it in database, now we do. Now we do have it, we created it by ourselves just on fly, just based on the addresses here and that brute force thing. As you can see, this work is quite simple. All you need to do, you just need to try this and that variant, and after some time, you will find that combination, which will show you good results, which will show you green map. And you can do this manually, like I did, but there is a way to do this, like an automatic way, to run brute force on it, and software will try all possible combinations automatically on fly. So you don't need to do that monkey job clicking on buttons and try it. And it will do this, of course, faster. And let me show how to do this. And of course, that mode is more advanced because it allows you to search not only for most common polynomials, but also for less common. So I have physical image. Now I bring this BCH element, and instead of going here and add code words manually, I will run code word analysis thing, code word analysis option, and full description of all options. Here we have on this slide. The first option here, it's page size. So you can set page size here. You know for sure page size already on this step, and there is no any problems here to set page size. And then we have option for addresses of payload area and parity area. And in this tool, we have option to set not precise address where payload area starts and where payload area stops, and the same for parity area. But we can see range of start for payload area and range of last byte of payload area. For example, well, usually we know where payload area starts, like it starts from 0, okay? But if service area is XORed and TCC is not, and data area is XORed, so data and service area is XORed, ECC is not, but ECC still looks like a noise, and we don't see clear borders between ECC and the service area, so we can't say precisely where is last byte of the service area, of the payload area. And we can say that it's, but we know typical structures, we know quite typical ranges, and we know full size of the page. So more or less, we can calculate that sizes approximately. And let's say that we know that 1024 bytes should be data area, and then approximately 8 bytes should be of the service area. So 1024 plus 8, it's 1032. But we're not sure about this because we don't see clear borders. So we can set here that last byte it's 1030, and first byte it's 1030, and last byte 1034, for example. So we set range, it's 4 bytes. And payload area in this case will start either from 1031 or from 1035. And last byte range will be, for example, we have, well, in this case, we will know pretty good the last byte. Let's say it's approximately 100 bytes. So it's going to be 1131 and 1135, like this. So that's the thing about ranges. Usually we don't need to do them, and I'll show you a little bit later how we can detect ECC borders quite precisely, quite good. So sometimes in some exotical cases, you may try to use this option. Well, actually, I will show you that exotical case when it works quite good. But normally you know quite good, quite precisely all these ranges, and you set just the same byte in this range. First byte position, last byte position, and so on. So let's do this for our case. So payload area starts from 0 and ends on 1031, right? Then parity area starts from 1032 and ends on 1073. Okay, so we set addresses of all the of payload area and parity area. Now here we can select which, how do we want to search polynomial. We can try to apply known polynomials here, which the polynomials which are mostly used for the BCH correction of NAND devices. Or we can search polynomial by degree. By degree means that we, for example, if degree of polynomial is 16, it will take, if you select it like this, so it will try all polynomials with the degree of 16. So it will take polynomials like x power 16 and x power 15 and so on, and so on. So it will take not only known polynomials, but all of them. And this process may take huge time, a long time, but you may probably find some polynomial which we don't have here, some very, very different, very new. So first of all, of course, you try to search by polynomials, by known polynomials. And if it fails, and if you still believe that this is BCH, you can try to search by degree, but usually it's this option is mostly for research. Usually if you will not find something by this method, you better ask our support team for help. Okay. Now that operations. So by default, it has checked most typical operations. So without any transformation, with inversion, with that most common bit rotation only. with inversion only, with bit rotation only, and with inversion and bit rotation. If it doesn't work, you can select all these options and VNR will try all of them. It will not add too much time, so in case if default selection doesn't work, you can try to select all of them. And here address, you can try to run analysis by within whole dump, so it will randomly take some positions in dump and will try to apply these things on the dump and check if it's correct or not. But if your dump is mostly empty, let's say that you have just several blocks of data within dump, it may not work. And then you need to set, because it will just not find that blocks with data, may not find. So in that case, it's better to set fixed address of that blocks with data. And then VNR will run this search on data blocks, on the blocks which you selected. But if you have a lot of data in dump, it's pretty full, you can leave this address. And now all you need to do, you just click to analyze, and very quickly it tried all that things. And it's here we have column weight. It's like a probability that this result is good. And if you have some result with a bigger probability than another ones, so it's you should try this code word. So we select it, we click add, and it's tasks confirmation. We click OK, and we came back to that window that we saw before with a list of our code words. So first code word is ready. For the next code word, we should add it manually because payload area and parity area will be different. If you remember, it's different. So we set payload area start 1074, and stop will be 1074 2101, then parity 2102, and stop 2143. We know polynomial already. It's here. It's 16,427. So I just selected, and I see that inversion should be used, and first bit rotation type 1. You see, R1 means that first type of bit rotation is used. So I add it, and again, since sizes will be the same for all another code words, I just use this button 1, 2, 3, 4, 5, like this. 8 code words for 8 kilobyte page size. And I can close this. Then I check ECC map. And if I see something like this, green colors, so that's all right. ECC works, and we can proceed the case. And of course, if you didn't do any mistake, you should see that green colors. All right, so that's how that code word analysis work. Now let's see another case. Open case. A SAM controller. So now we will just do the page layout thing and code word analysis for 3 more cases, and maybe we'll see some peculiarities. Okay, so SAM controller. I'd like to remind you that SM controllers have this structure. So data area, then ECC, data, ECC, and so on until the end. And in the end, we have service area and ECC of the service area. So let's do that page layout. Page is undefined. We know that we have, most probably we have 1024 bytes of data area, because you see page size is 8 kilobytes. So such page sizes usually use 1024 bytes of data area. So I just set here 1024 like this. And now it comes to uncertainty. How many bytes of ECC I have here? Because, well, actually I can see some borders. See, ECC looks quite noisy, and then I have some patterns. So I guess that ECC finishes, okay, may finish here, but it's not very much clear. And how can I detect ECC size precisely? There are several ways for this. The first way is just a math calculation. I can take, I know that size structure of EC of the page of some controller, it's a data area plus ECC, data plus ECC, and so on. So if I will take total number of bytes which are occupied by data area plus ECC. So it's this amount bytes. This is last byte of data area plus ECC, and it's 8527 byte. And so in total we have 8528 bytes, right? 8528, because we start to count from 0. So 8528 bytes I have for all data areas and all ECC areas. Now let's think how many data areas may be located within these 8528 bytes. How many data areas? Taking into account that one data area is 1024 bytes. So in total I have 8,000 of bytes. One data approximately. One data area is 1,000 of bytes. So in total, yeah, right, within all these areas I may have 8 data areas. So I understand that I have within my page, I have 8 periods of data area plus ECC. So I just, let me share this calculator. So I just take 8528 bytes. That's total number of bytes which belong to data area plus ECC. I divide it by 8 because within this area I may have maximal 8 data areas, 8 payload areas, or 8 periods. I divide it by 8 and I get 1066 bytes for one period of data area plus ECC. Now, since I know that data area is a standard and data area has standard size, it's 1024, all I need to do, I should take this number and minus 1024 bytes of data area. And that's it. It's 42 bytes. So that's the way how I can very quickly and easier detect ECC area size, 42 bytes. There is another way and it's quite cool, let's say. Let's say that I don't want to calculate it like this for some reason, or actually I can use this approach also for some another cases where, like for, I don't know, for FISM controller where I have another structure and I can do this straight calculation. There is another way how I can, let's say, highlight ECC areas only. So you can use this approach, and you may use this approach on XORed dumps only, when you don't see that clear borders between ECC areas and data areas. And to do this, we can do next thing. We can run that XOR analyzer on physical image, run auto detection, and it will show us blocks. If you remember, it will show us blocks which are most probably have a XOR key inside. But we don't look here now for XOR key exactly, but we look for some, typical pattern within this for this dump. Well, usually a typical pattern, if there is a pattern for the dump, would be XOR pattern, but in fact it could be something else. So in this case, it's actually XOR key pattern. And now have a look. If I will take, for example, this block with this pattern, and I will extract this block. So I select only this one block, make right click and extract current block. I have this block now in this offset. Have a look, it's here, right? And if I will XOR now this physical image with this, let's say, typical pattern, and I don't need to do any preparations and other preparations now. I don't care about bit errors, about page layout. I'm actually now trying to figure out page layout. So when I do XOR transformation of physical image with some typical pattern of this physical image, when this typical pattern will be applied on another typical patterns within this physical image, let's see what's gonna happen. So now it's a result of that extracted block applied to the dump. And it's just now XOR key is kind of removed. And when I apply one typical pattern, block with one typical pattern for the whole dump, I may find many places where that applying will show me these patterns more clear, more precisely. And you can see it on this slide. So we have these data area patterns, then noise, because ECC looks like a noise always, and it's not possible to, well, probably this block, by the way, when you apply block one data, when you XOR one data to exactly the same data, you will get just once. So probably this block, it's the block which I extracted, and that's why we have here just once. But for another blocks, I will just recognize more patterns. So I don't do now unXORing or XORing the dump. Now I'm just trying to, let's say, highlight patterns to see that patterns more clear, more precisely. And that patterns will show me areas of ECC, because ECC will always look like a noise. And let's see, for example, here, I have this line is going until this byte, then this byte is the first byte of noise. And then the line starts from here. So this is last byte of the noise. And have a look. I got again 42 bytes. So this approach, it's pretty commonly used by us when we don't see any patterns, any lines, any columns in the dump, and we want to make it more visually recognizable. We just search for some specific pattern or common pattern for this particular dump. Usually this is XOR. And with this XOR thing, we can like do it more clear, and the structure of page will be more recognizable, like now. So this is just for analysis. It's not an XORing, it's not for recovery, it's just for analysis, approach for analysis. Okay, so we remember that this is 42 bytes. ECC is 42 bytes. Now we can just remove this and proceed with the layout. So data area, then ECC is 42. And then it should go the same like this until the end. So I copy these two structures and then make right-click, paste till the end. And there we go. Now I have for full page described here, and it's just necessary to do ECC, LBN and header and so on. But that's another story already. So page layout is done. And now it's time for ECC, right? So let's do this. Connect ECC, and I'm not going to use this manual way. I will run automatic brute force, let's call it like this. So I connect it like this. ECC codeword analysis. So first byte is 0, last byte it's 1023, and then 1024, and last byte is 1065. 1065. And that's it, basically. Analyze. Something is found. Probability is quite low, but let's check it anyway. Yeah, there is no another versions, another variants. Okay, so it's here now. ECC map. There are bit errors and bad areas in this this chip, but most of pages are still correctable, as you can see. So that means that Codeword is still good. If everything is right, then it's bad. If it's like this, it's okay, it's good. Even if you have something like, like this, it's just really bad areas, really bad blocks of the chip. You should evaluate this in general, overall. And if in general it's okay, then Codeword is good. So what's next? The next, you need to add codewords for another payload areas. And to do this, we can use just this option. Add codeword from selected. 1, 2, 3, 4, 5, 6, 7. All righty. And that's it. So Codeword is ready. And there is one thing which I told you I want to show. When it's good to use this Codeword analysis. Service area of SM controllers. If you remember, first several bytes here belong to the service area. Then rest of the bytes belong to ECC of service area. If these bytes for all pages within one block are the same, I mean, we don't have any LPN here, it's stable. They're the same. So ECC will be the same. And as a result, it will look just like a lines here. And it may be not that much clear where is service area and where is ECC. And sometimes you may want to run ECC correction for service area too. If like you have quite damaged device, like this one, for example, and you worry that LBN will be corrupted, you may try to run ECC correction for service area. And here you don't see that much, that clear borders of where is payload area and where is service area. And for this case, those ranges may help us. So now let's try to set it. So payload area starts from exact number. It's 8528. It's first byte of undefined area, first byte of service area. 8528. Then last byte. We don't know which one is the last byte of this service area, but we can assume that it's approximately 1, 2, 3, 4, 5. Okay, let's say that it's 4, 5 byte approximately. Maybe byte number 4 is the last one. Okay, so we assume that more or less it's 4 bytes. And then let's just add the range like 4 minus 1 and 4 plus 1. So then the last byte of this range, 8528 plus 3 will be like 28, 29, 30, right? It's 3 bytes, sorry, 85, 30. And the last byte, let's say 85, for example, 33. So I said here we can see, I mean, here in byte position, we can see number of bytes where the mouse is now. So I said that payload area starts from this byte, it's 8528, and ends on 1, 2, 3, 4. So that's, I support this last one, but I just added the range. So from here, 8530 and until 8532. Well, I said 33, it's okay. Would be, but let's say 32 to speed up the process. But it may not work, I don't know yet. Maybe we will have to increase the range. And the parity then will start from 8531, right? Next byte from this one. And from 8533, 8533, like this one. This will be the range of parity. And last byte will be also known. If I zoom it in, I see that this is the last byte, and the number is 8553. See? So I'll set 8553 for both. And it seems to be okay now. I can click to analyze. it's trying different combinations, and it found nothing. Okay, let's add more polynomials to try. And maybe let's add all that bit rotations, all possible combinations. And oh, and now it could find it. There are many results with the same polynomial. It's 285, this one. Same transformation of data. Wait, it's just here we have addresses in bytes, and here we have addresses in bits. I believe that it's more or less plus minus the same addresses, maybe just several bits difference. So most probably that this code word will be the good one. And I can edit it. Yeah, and now I have it here for the, now I have code word here for the service area of a SAM controller. Let's check if it's still good, because, well, actually it should be good, because this map shows the worst result. And if I still see quite green colors, that means that this code word still works. But let's just make sure and leave only this code word. Oh, and you see that service area, it's quite in good condition. Most of service area is good, and just some pages have light green color. So they have bit errors. And most of service areas have no bit errors at all. Okay, so that's a very good example how we can use this code word analysis, and when we may use those ranges, when we are not sure. Oh, by the way, let's see. So it's 3 bytes of service area. One, two, three. Oh, so this one was, I thought that this one will be the last one, but no. First 3. Well, actually, the first one is the header, then 2 bytes for the LBN. And this 1 byte may be actually just empty, and service area may start from this one. Well, anyways, code word works, and we could detect borders of service area and ECC for service area here when it's not that much clear. Okay, questions? All right, now let's do the next case. I think it's gonna be more quicker, because most of things I have shown you already. Okay, now it's AU controller. Let's dig in. Well, this is kind of artificial case. We have a lot of blocks written by zeros. Let's take some noisy area, pretending that this is the real case. Oh, it's here. So AU controller fully well, not fully, but it's XORed. Service area is not XORed here, and that is good. It's here, and we can start. We can, by the way, just quickly check position of service area, and it's, as you can see, approximately 1024 bytes. So it just proves that first service, that the data area here is 1024 bytes. So I said data area 1024 like this, and I have it here. Then I have 2 bytes of the service area. Service area 2 bytes. Like this. Then I need to set ECC size. I can't see any borders now, so let me just calculate it like I did in the previous case. So I make left click in the first byte of that period, and then I scroll it to the next service area. It is here. Right click in the last byte, and I have 1136 bytes selected. 1136 minus 1024, it's 112. So 112 bytes belong to ECC here. I do double click, ECC 112. Okay. And then next data area should go, right? Next data area, and you see it's here. So once I see colors on correct positions, I understand that so far so good. And it's so far so good. And I can proceed. So after the data area, I have next service area. Copy, paste, and then next ECC area. Copy, paste. So you see that the first 2 periods, well, first period I don't know yet the sizes and structures. I just detected and said on second period I check that I'm correct, and there is no any mistake. And once I found this, I can just select this period, click Ctrl+C, and here paste till the end. And I have it until the end. And there seems to be some mistake. Because as you can see, I have some data here. Okay, all service areas seems to be on the right position. So this area is just some unused area, empty area, which looks like a noise. Because you see that on another places here, for example, No, it's well, yeah, that's all right. So that empty tail of the page here looks like such kind of noise. We can see it here. Yeah, so this is data area, then last service area, then last ECC, and then some pattern. And in case if we have a pattern in here, so we still see the same pattern in the tail. If we have data, I mean noisy looking data, we see this pattern, this data in the tail of page. So it's just peculiarity of reading of this chip. Okay, so ECC is no, page structure is done. It's all correct. We can prove it by service areas. You see that service area is in correct position. Then we have ECC, and here we can see that it ends on the right position, because after we have just some pattern and it's just a noise. For some reason, chip brought this data to the reader when the reader reads its pages. So that's why the tail of page looks like this. Okay. Page is done. Now let's do BCH. BCH, where is it? It's here. And I believe that it's gonna be really quick now. Now I open this to see addresses, drop it to here. ECC Codeword analysis starts from 0, goes to 1025, 1025, then 1026, and last byte of ECC 1137, 1137, and that's it. Analyze, and I have some code word. Add, yes, have it here. Let's check the map. In the beginning, I have such pages. It seems to be some, it could be some buffer pages or firmware. And then it looks like this. So Codeword works. And let's add next ones. Page size here, it's 16 kilobytes, so I need to add 16 code words. And it's kind of slow now because it's recalculating each time ECC map. It looks like I did too many clicks. Okay, let me remove it. Okay, 16 code words. And ECC, well, chip is kind of pretty damaged. I think read retry should be applied. But the thing is that ECC is good. ECC works. Okay, so that was AU controller. And the last one will be SanDisk. Okay, let's refresh how SanDisk structure, page structure looks like. SanDisk has 14 bytes of the service area in the beginning, so you see it's different from another devices. Then it has 1024 bytes of data area and then some amount of ECC bytes. Okay, let's find it out, how many bytes it has for ECC. So I open the dump, I go to some area with the data. And well, actually here I can try to apply that another approach with the XORing whole dump by some typical block. So how do I do this? Physical image, XOR analyzer, start detection. Now it's just some garbage blocks, and yeah, this is kind of, this one looks to me quite typical. It seems to be XOR key. So clear all use, select just this one, extract current block, then bring this XOR. And let's see what we get. And we can quite clear see now ECC, oh, sorry, service area. And then when we scroll the page horizontally, we can very clear see ECC. So let's check these numbers. As we supposed, service area has 14 bytes, because you see this line, this pattern starts from this byte, and this byte is number 14. So the last one is this one, and we start from 0. So in total, we have 14 bytes for service area. So I can do like service area 4 bytes, or sorry, 14. And it's here. Then I have data area 48 bytes. And now let's just check that this is correct. Oh, I set 8 data areas. It's wrong. Remove record data area. Looks like this. Okay. And we see the data area starts right before the noise, and the noise, it's their ECC. Now let's check how many bytes we have for ECC. So this is the first byte of ECC. And this is the last one. And it's 146 bytes. ECC 146 length Okay, and then we have next service area, which is again 14 bytes, the next data area, next service, next ACC. We can just try it on next period once. And since we see that it's good, then we can make option, we can use option paste till the end. And we can see that we have pasted this until the end. And there is no any empty space on this page. So it's totally full. Okay, page layout is done. And you see that I did it on this XOR element. But in fact, I want to remove this because it was just for analysis. Physical image still doesn't have structure. How can I copy this structure from here to here? I can make it like this. Copy structure and paste. So now I have structure here and I can delete this thing. And you see that its physical image has it now. Okay. And the last thing, it's BCH. ECC. Okay, let's open this again. Bring it here, then ECC. Codeword analysis. First byte starts from 0. Last byte, it's 2061. It's last byte of data area. And TCC starts from 2062 and goes until 2207. Let's analyze it. Okay, and we have it here. And let's check the ECC map. It's a fixed chip, so it's almost all whole. It's almost all green. And let's add another codewords. We have here 16 kilobytes page size, but since one period it's 2 kilobytes, so we will have 8 codewords. This one will be not necessary already. And that's it, guys. This is how we do. This is how our users actually can do BCH reverse engineering for some unsupported devices.